Okay, in this lecture, we're going to talk about phase diagrams, putting together everything we've learned in the past few lectures on vapor pressure, supercritical fluids, and intermolecular forces. So, phase diagram. Basic definition is it's really just a graph of pressure versus temperature. Okay, so on the y-axis here, you have pressure going up, you're increasing in pressure. On the x-axis down here, you have temperature. Going to the right is temperature. Usually this will probably be in Kelvin or Celsius. The pressure might be in atmospheres, torrs, millimeters, mercury, Pascal. It kind of depends on what country for what pressure is the normal pressure to be used in that context. So a phase diagram really puts together a lot of information about the different phases of matter and when they are present at different pressures and temperatures. And one thing you'll see is the solid phase. All of this over here is a solid phase, and it's separated from all of this liquid phase by this line. And actually, there should be an arrow on the end of this line. It goes up essentially forever. And all of this solid and all of this liquid is separated from all of this vapor or gas phase. You'll see those terms interchangeably for gas and vapor. Solid, liquid, gas. But you also have this out here. And we talked about this lecture last time, or this topic last lecture, supercritical fluids, right? When you're beyond this critical point, you aren't really liquid or gas. You're some new phase of matter that is a combination of the two. It is not a mixture of liquids and gases, but a whole new state of matter. So we really have solid, liquid, gas, and supercritical fluids. Now, what's useful is that there are pressures like atmospheric pressure, maybe at sea level. This is the pressure we care about. And maybe it's sea level and it's 760 torr. Maybe that's my unit on my pressure axis. And at this pressure, if we walk over to here, this dividing line that separates solid from liquid, well, this will be the melting temperature. So whatever temperature this is at, coming down here, will be my melting temperature. And likewise, if I walk over to here, this right here, that separates liquid from gas, well, that is my boiling temperature or vaporization temperature. And so from this simple diagram, you can look up what pressure you're at. If you're at sea level, maybe it's 760. If you live a mile high, then maybe your pressure is slightly lower, like down here, 630 when you're a mile high. And what happens is, well, now your boiling point has shifted to this new lower boiling point you could call TB prime. And this is boiling point suppression. Okay, so based on walking around this diagram, you can predict the temperature things are going to boil at. You can predict the temperature it's going to melt at. But remember, all of this is for one certain type of substance. Okay, this is a phase diagram in general, but you're going to have one of these for water. You're going to have one of these for sulfur hexafluoride. You're going to have one of these for carbon dioxide. And they're all going to be slightly different, but they're all going to have solid, liquid, gas, and supercritical fluids. They're also all going to have a triple point. And a triple point is not something we're used to seeing in nature because it's a very particular temperature and pressure. So this pressure exactly, and this temperature exactly. When simultaneously I have those two conditions for this material, then I can have a coexistence, right? And this coexistence at this point is solid, liquid, and gas all at once. And you can look up some really cool videos for this for water or other compounds. Seeing, solid and liquid coexisting is normal. We see ice water. Liquid and gas, we have boiling water on the stove. That's fine. But getting all three in equilibrium and present at the same time really only happens in an equilibrium at this temperature and pressure. So that's the triple point. These are the different phases, solid, liquid, gas. Okay, but you also have the critical point, which we talked about last lecture. Beyond this is when you enter the supercritical fluid. The last thing I want to point out is this curve for the liquid gas separation. This shape is exactly the functional form of this Clausius-Clapeyron equation we learned about in last lecture, right? So we had this exact relationship for two pairs of temperatures and pressure, but this functional form, this logarithmic pressure dependence as a function of 1 over t, well, essentially that is the shape of this curve. So this is the vapor pressure curve that we talked about in previous lectures. And so it's showing you how the vapor pressure changes as a function of temperature, right? The higher you go in temperature, the more to the right you walk, the higher the vapor pressure, which makes sense because the higher the temperature, the more the molecules go to the gas phase, and so more molecules can exert a higher pressure in said gas phase. Okay, so that's your way around a phase diagram, solid, liquid, gas. You have a vapor pressure curve, you have a triple point, you have a critical point, and that's basically all the information you can get from this. Now, I want to look at certain phase diagrams, 2 examples, the first being water. And I want to look at water not just because it is the most important compound in the universe, but because it has some really peculiarities, okay? 2 things I want to point out. The first thing I want to point out, just going to put an arrow on here because this line pretty much goes up for a long time. The first thing I want to point out is this critical point. This critical point is really a high temperature compared to other substances. Most substances don't have critical points in the 600 or 700 Kelvin, right? Water does. And this critical point, you'll remember, is the point beyond which you cannot compress the liquid, you cannot compress the gas into a liquid phase, right? If you're over here in the vapor phase or the gas phase, increasing the pressure is walking straight up the diagram, and you convert to the liquid phase, right? If you're here in the gas phase at 580 Kelvin, increase the pressure, you can make it a liquid. And you can keep doing that. But beyond this critical point, right, if you're at this temperature and you try to compress it and increase the pressure, it never turns into a liquid. It just remains as this supercritical fluid. And usually that's not the case. Usually this critical point is going to be a much lower temperature, somewhere around here. The reason it's so high and it's elevated, greater than 600 Kelvin, is because of the hydrogen bonding in water, right? Again, it's these strong forces between 2 liquid water molecules, this hydrogen bonding, that is especially strong compared to dipole-dipole forces or dispersion forces. And so it really takes a lot of energy, a lot of temperature to overcome this hydrogen bonding network to the point where you cannot compress a gas back to a liquid. So that's one thing, the critical point. The other thing I want to point out, I guess, about the critical point is the curve stops, right? In my previous phase diagram, we put an arrow on this. We did not put an arrow here, right? Because the separation between liquid and gas stops in the supercritical fluid. Also here, it stops. This is all supercritical fluid. This line keeps going up, okay? There is no like supercritical solid liquid thing here. This goes up forever. There's always a distinction here between solid and liquid. The other thing I want to put out here is water has a really unusual solid liquid line. It's not unusual in the fact that it goes up for a very, very long time, right? It's unusual in the fact that it is negatively sloped. Almost every substance has a solid liquid line that looks like this, positively sloped. Water is one of the few that has a negatively sloped line. Okay? So while that's really rare, it's actually really beneficial. It's the result of this property of water in the solid phase to set up these sort of cubic arrangements of the hydrogen bonding network so that you have all this solid ice empty space in here. And so when you're a solid and you can set up this hydrogen bonding network, you get all this space in the middle where there is no water. So solid water is less dense than liquid. When it's the liquid phase, you sort of overcome these hydrogen bonds, and they're vibrating around a little bit more such that they can fill in this gap. And so liquid water is more dense than solid water, right? And that's the reason solid water floats on liquid water. Solid water is less dense. So this negative slope here for water is really unique, but it is really important for the basis of all life, really. So increasing pressure doesn't matter, if you're a liquid, doesn't matter where you are in the liquid phase. Increasing the pressure walking up on this diagram does not turn the liquid into a solid. Okay, so as pressure is increased, the melting point actually decreases, and you can't just increase the pressure to get it to go to the solid phase. As we go up to higher and higher pressures, right, this line is moving to the left, and so the temperature is moving lower. Okay, so as the pressure is increased, the melting point decreases. Okay, so that's pretty unusual for things. Usually in the liquid phase, you should be able to press on the molecules and get them to pack more closely together like a solid. But ice isn't that way because you only have this open space in the solid phase, right? In a liquid that is not water, usually you can push the liquid water molecule or the liquid molecules closer together and get them to pack more densely into a solid network. Not the case with water. Okay, so it's this negative slope line that is really important for governing a lot of existence of life, right? If it was the other way, then ice would freeze and not sit on the top of water and not insulate the water from continued freezing. So our lakes don't freeze completely top to bottom because of this negative sloped line between solid and liquid water. The last phase diagram I want to look at here, now that we've seen some weirdness here, is carbon dioxide. And carbon dioxide is kind of a cool one because you actually don't exist at the liquid state ever at atmospheric pressures that we're used to, right? So we live our life down here around 1 atmosphere, 760 torr. Yes, you can climb a mountain and go down a little bit to maybe 0.8 torr, right? You could go, down underwater and maybe do some experiments, and maybe you're at 1.5 torr, but you're never really going to get to 5.11 atmospheres. And as long as you're below 5.1 atmospheres on this logarithmic scale, you never exist in the liquid phase, okay? So all of human life is down in here. Maybe not these low temperatures, but it's all at these low pressures, right? So at pressures at which we never experience liquid or supercritical CO2. What this means is that, at room temperature, of course, 20 degrees Celsius and atmospheric pressure, we're right here. CO2 is a gas, but we know that. We breathe out all the time, exhale CO2, it's a gas. But if we cool it all the way down, we expect that gas to condense, right? But it doesn't. The phase diagram tells us if I cool this, I never enter the liquid phase. The liquid phase is way up here. I never enter the liquid phase. So as I cool this gas, eventually it just solidifies, and it solidifies at like negative 83 or so Celsius, right? This is the deposition point, it's called. Sublimation is solid to vapor. Vapor to solid is deposition. So the deposition point is around negative 80 degrees Celsius. So you never experience the liquid. This, for example, is called dry ice. When you buy this dry ice from the grocery store or some vendor, that is just solid carbon dioxide. As it warms up, right, it's at atmospheric pressure. You're using it in your cooler, right? It's warming up, it's walking to the right, and it turns into a vapor. It never enters the liquid phase, so cleanup is a breeze. You don't have to worry about slopping up all this liquid water because it's not water, it's carbon dioxide. As it heats up, it vaporizes. Okay. The other kind of cool thing about CO2 is it has a reasonable critical point in terms of temperature. Okay. It takes a lot of energy to change the temperature of something, but it doesn't take as much energy to change the pressure. So although this pressure is kind of high for the critical point, right? Up here at like, I don't know, 70 or 80 atmospheres, the temperature is not that warm. You have to slightly warm it, and you just have to really pressurize the carbon dioxide. And what's cool is if you take this about room temperature carbon dioxide and compress it a whole bunch, you enter this supercritical fluid, right? This SCF. And supercritical fluids are actually really, really useful. CO2 in particular as a supercritical fluid is used as a dry cleaning agent, or used to be. I'm not sure if it still is. It's been a while since I've dry cleaned things in my laboratory, but you could dry clean with CO2, and people often did. The reason is because CO2, right, is cheap. You can get it to this supercritical fluid pretty easily. And then what's nice about a supercritical fluid is it really combines the properties of liquids and vapors or gases, right? So this supercritical fluid of carbon dioxide has the dissolving power of a liquid, right? Think of like a detergent. The liquid properties let it really dissolve things. So it can dissolve stains, but it has the penetrating power of a vapor. It can get everywhere, it diffuses everywhere, it is like a gas. So that's a practical application of a supercritical fluid. Here for CO2, it exists at a reasonable temperature, so you just really pressurize the heck out of it, get it to the supercritical fluid state, put your clothes in it, and now you're able to dissolve stains, and you have the penetrating power of a gas. So those are phase diagrams. There's one for carbon dioxide, a little bit unique, and water, very unique with regard to this negative sloped line. Just realize the terminology here and all the information you can get out of these really, simple looking figures at first glance that contain all this information about melting, boiling, subliming, supercritical points, and vapor pressure, temperature dependencies, triple points, all of this in one nice, neat little figure. So that is our discussion of phase diagrams. If any of this was confusing, make sure you go back and watch the previous lectures on intermolecular forces, viscosity, surface tension, supercritical fluids, vapor pressures, etc., etc. Otherwise, that'll do it for this lecture. See you next time.